Physics and mathematics are in the modern day utterly inseparable. In previous centuries, physicists resorted mainly to physical observation and experiment when forming theoretical frameworks. Think of Kepler analysing the orbits of planets to discover their elliptical nature, or Newton watching an apple fall to the ground. However, in the modern era, the boundary between theoretical physics and pure mathematics has been blurred. One example is string theory, in which physical problems have forwarded pure mathematics, and in the same way, problems in pure mathematics has forwarded physics. I'm often reminded of a famous quote from Einstein, not long after he published his theories on general and special relativity. Since the mathematicians have invented the theory of relativity, I do not understand it myself anymore. Which shows just how embedded mathematicians have become in modern physics. My goal is to explore and hopefully give you some insight in one of my favourite fields in mathematics. So, the only logical place to begin is by explaining exactly what we mean when we say the words group theory. Group theory is the study of algebraic structures known as groups. Now, that might not be very helpful and a lot to unpack, so I'll go through and explain each point individually. First, what on earth do we mean when we say algebraic structure? Well, it has a precise definition. We begin with a non-empty set of elements. We denote a set with these curly brackets here. The elements of a set could be anything really: numbers, shapes, names, animals, and anything else you could think of. From there, we define a collection of operations on said set, which are usually binary, meaning that it takes two elements from the set as inputs. Some examples include the dot product or inner product, addition, multiplication, etc., etc. Finally, we have a finite set of axioms that these operations must satisfy, which are fundamental assumptions that we take to be true, but we need not prove. Okay, so now that we know what we mean by algebraic structure, we can also define exactly what we mean by the word group. The most simple and bare bones definition of a group is a set along with a binary operation, often denoted star. It must satisfy the following group axioms. Closure, i.e. given two elements of the set, if we apply the operation, then we get another element of the set. We also must have an identity element, which when applied to any other element of the set, gives exactly the element we started with. A physical picture of this is to say we start with a set of elements, coloured cubes for example, and a tap which represents the identity element. If the operation was the process of running these objects under the tap for a certain amount of time, applying this operation and leaving them there to dry would give us the cubes we started with. There exists an inverse which gives the identity element when paired with their counterpart, and finally we must have associativity of the operation, so A star B star C is equal to A star B star C. One very important subclass of groups are the abelian groups. This is when the operation is commutative, i.e. A star B is the same as B star A. One example of a group includes the integers, which forms a group under addition. It is also abelian. Let's now delve deeper into the integers and actually show that it obeys the required group axioms. So, to begin, the integers are an infinite set of numbers from negative infinity to infinity. Under addition, the identity element exists and is 0, as clearly a plus 0 equals a, as required. The additive inverse also exists and is called minus a. Clearly, a plus minus a is equal to 0, i.e. the identity. We also have associativity of the operation, as we have a plus b plus c is equal to a plus b plus c. We clearly also have closure, since adding or subtracting any integer from another gives another integer. To see that it is abelian, we must use the well-known fact that we have known from childhood, that a plus b is equal to b plus a. Hence, the integers under addition form an abelian group. Now that we have looked at the integers in more detail, I shall continue by giving another example of a rather important group in group theory, the dihedral group. The dihedral group we'll be looking at is D6, which is on the thumbnail of the video. It is the symmetry group of the regular hexagon. You might be thinking to yourself, how do the symmetries of a hexagon lead to a group? However, I will show you the steps and the logic of why it must be so. It will also hopefully give a more intuitive and physical understanding of groups. We begin by drawing a regular hexagon and labelling 6 vertices A through F. We denote an anti-clockwise rotation of pi over 3 radians by R and a reflection about the AD axis by S. It can be shown that a reflection about any other axes, for example BE, the lines I've drawn here on the hexagon, can be written in terms of R and S. I highly recommend that you whip out a piece of paper and give it a try. We can see that S, SR, SR squared, SR cubed, SR to the 4, and SR 5. Here, the superscript can be thought of as how many times I apply the operation, not a power, generate all the reflections of the hexagon. The identity in this case can be thought of as applying no rotation or reflection. But notice that if I rotate this hexagon 6 times, then I get the identity. This way we can write r to the 6 is equal to e, where e is the identity of course. Similarly, if I reflect this shape once, and then reflect it again, once again across the AD axis, then we notice that I get also e. So in this case, I can write s squared equals e. So we have found the identity. Next we notice that if I rotate the object 5 times, i.e. r to the 5, and then rotate it once more, I get e. Thinking about it for a second, this must mean that r to the 5 is the inverse of r. Thus we have inverses. Now, if we multiply, in air quotes, 2 elements of the group together, we get another element of the group. For example, if I multiply r with r to the 3, I get r to the 4. This is basically saying that if I rotate once, then rotate 3 more times, that's the same as rotating 4 times. I suggest that you try and show this case for the other elements. Associativity in this case is rather obvious, as doing rotating, reflecting, and then reflecting is the same as rotating and then reflecting twice. Notice that unlike the last example, this group is not abelian, as rotating and then reflecting is not the same as reflection and then rotation. If you want to learn more about dihedral groups, I highly recommend Michael Penn's great video lectures about them. He goes into a bit more detail and gives some more examples. Dihedral groups, while simple, are vital in fields such as chemistry, where symmetries of compounds play a significant role in their properties. This concludes my short introduction to groups. It was hopefully given you a brief glimpse into a very deep and rich subject, and shown how the abstract nature of group theory makes an extremely wide-reaching tool. In the modern world, group theory has uses in coding, chemistry and physics. Even a Rubik's Cube can be modelled using group theory. As this is part 1, I wanted it to be a light but informative foundation, onto which we will continue to build our understanding and delve deeper into the topic, covering some important proofs and theories which will be useful when it comes to applying it to physics. Anyway, I hope you've enjoyed. Thanks for watching.